All right, so two geometric figures. We're talking about congruence and transformations. Two congruent figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that map one of the figures onto the other. Remember, congruent figures have the same size and the same shape. So remember, the ones that we've talked about right now, we have talked about translations. We've talked about reflections. And we talked about rotations. So another name for a rigid motion or a combination of rigid motions is a congruence transformation because the preimage and the image are congruent. The terms rigid motion and congruent transformation are interchangeable. So I noticed whoever did the homework, they didn't choose anything from example one, so I didn't show it to you. It was just kind of showing you where you could see which ones were happening. So, and it's kind of like what we're going to do with this one here too. So, example 2, describe a congruence transformation that maps quadrilateral ABCD to quadrilateral PQRS. So that means that we're going to move this one here. We're going to try to move it so that it looks like this one here. Again, using a translation, a reflection, a rotation, or a combination of both. So if you choose one of the points here, all right, and again, kind of think of what I did yesterday. I want you to kind of have to use your imagination here. But if I move that one over, it's going to map onto S. So we know that it has to go over to this one here. So if I moved it over and up, it's not going to do anything. I would still have to do something to it, rotate it or reflect it. All right, so remember what I talked about yesterday? All right, how if I put a square here, now I'm in quadrant 3. And again, now you're going to have to use your imagination a little more than what I did the other time. All right, now I want you to think, if you rotate it counterclockwise, it's going to go this way, right? It's going to actually go this way. Sorry, I keep forgetting I have to mirror this too. So it's going to go this way. All right, so we know that it's going to go this way here. So if you think about it, if I move it just one, it's going to be the same. Another way to remember it is what we had yesterday. If we said D was 1 and negative 2, it would go to where S is, and S is 2 and negative 1. So if S is 2 and negative 1, all right, remember if this was your A and this was your B, it looks like what we're going to do is we're going to have negative B here, right, because a negative 2 is a positive 2, and we'll have a negative A here, all right? So if you recall from yesterday, and you might have to remember, so either rotate it counterclockwise, all right, which is what the arrow is showing there, and look at what we did yesterday. So you should see that it's 90-degree rotation. About the origin. Okay, so compositions of two reflections result in either a translation or a rotation. A composition of two reflections in parallel lines, there's a key, parallel lines, results in a translation as described by the following theorem. So the reflections in parallel lines theorem states if lines K and M are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. So if A double prime is an image of A, then A double prime is perpendicular to K and M. So it's saying that this whole thing right here is perpendicular to K and M, and they're showing you that they're perpendicular by those boxes. All right, and A double prime is equal to 2D, where D is the distance between K and M. So basically what they're saying is whatever's here, the rest of this right here, this part from here and this part from here, those two added together would also be D. All right, so kind of think about that. And you can see it here in example 3. So in the diagram, a reflection in line A maps PQ to line segment P prime Q prime. A reflection in line B maps P prime Q prime the line segment to line segment P double prime Q double prime. Also, PJ is equal to 3 and LP is equal to 8. All right, so name any segments congruent to each segment. So PQ and PJ and QK. So if we look at PQ, PQ is this one right here. So remember, PQ is being reflected over K. So we haven't changed the size or the shape. It's still the same size and it's still the same shape. And then the P prime Q prime line segment flips over, is a reflection over line B. So again, that hasn't changed size or shape. So a reflection, again, as a reminder, a reflection is a congruence transformation So line segment PQ is congruent to line segment P prime Q prime because again it hasn't changed size or shape, which will make it congruent to P double prime Q double prime. So that took care of the first one here. The second one, PJ. So if you look at this here, PJ would be this segment here. So from P to J. From J to P prime, if you look at it, it even kind of looks like it's the same distance. Not that we're supposed to assume that, but what they told us, we can say that PJ is congruent to PJ, P prime J. Okay. And then by the same token, we have QK. So that would be that one right there. Again, I'm just tick marking it so you can think. So if I flip it over, the distance from QK is the same from Q prime to K. So those two are going to be the same. So we can say that QK is going to be congruent to Q prime K. All right, so I did all three. That's what they asked for. Great. Okay. Does JK, remember now we're talking distance, there's no line segment over it. So does the distance of JK equal the distance of LM? And explain. So if you look up here again, I kind of told you. So I'm going to tell you it's yes. all right? Because we know that Q double prime, so that's this whole line segment here, right? So that's Q double prime. So we know that Q double prime is perpendicular to both K and M. And we just talked about it when we said that. So there A double prime is our Q double prime. Okay. So since we know that JK, line segment JK, and line segment LM, all right, since we know that these two were already told us they were perpendicular, I just told you that those two right there were perpendicular, right? So what has sides that are perpendicular, it has to be a square or a rectangle. I haven't told you that it was square, so you have to assume it's rectangle unless I tell you all sides are the same length. But we know that JK and LM are opposite sides of a rectangle. And if they're opposite sides of the rectangle, we know their distances are the same. So we can say that JK is equal to LM. And then finally, what is the length of P double prime? So if we look at it, P from P to P double prime, by our definition, is equal to 2 times the length of JL. Remember, JL is this length here, and above here they called it D. So this length from here to here is D. But remember, the length from P to P double prime is 2D. So if the length from PJ is 3, and the length from L to P double prime is 8, these two here are also 1D, because remember, the total length is 2D. So if that's the case, I can say it is equal to 2 times, well, JL has to be 11, right? Because if this is 3 and 8, that's 11. This also has to be 11, so 2 times 11 will give you 22. It'll be units. Okay? And so we have 2 terms so far, which is pretty good. We've only been in this for 4 sections, and we've only had 3. Remember, we had a lot of theorems. So on this one here, it tells us composition of 2 reflections and intersecting lines result in a rotation as described in the following theorem, which is the reflections and intersecting lines theorem, which states if lines K and M intersect at a point P, so lines K and M, so here's our K, here's our M, intersect at a point P, all right, then a reflection on a line K followed by a reflection on a line M is the same as a rotation about point P. Okay, so the angle of rotation is 2 times x degrees, where x degrees is the measure of the acute. There's a key thing right there. Acute. So remember, acute means what? Small, right? It's a small angle or right angle. So it can be acute or it can equal 90 degrees. So that's where x is the measure of the acute or right angle formed by the lines K and M. So our last example here is in the diagram. The figure is reflected in line K. The image is then reflected in line M. Describe a single transformation that maps F to F double prime. All right, so it says it is reflected in line K. That was one of the things they just told us above. And then it's followed by a reflection in line M. All right, again, they're not always going to be K and M, but what we have to remember is that they make a point here. All right, so those two lines intersect at a point. So by the reflections in intersecting lines theorem, so when you look at your homework, you'll notice that I'm kind of being wordy here. A reflection in line K, so basically just stating what the theorem said, followed by a reflection in line M is the same as a rotation about point P. Okay. Now remember, they told us that the angle of rotation is 2 times x degrees. So now they gave us 58 degrees. If you want to think about it, this whole thing is a straight angle, right? So this one here would be 122 degrees. But which angle did they tell us to take? They told us to take the acute angle. We know that 122 degrees is not acute. So the only one that's acute is 58 degrees. So we would then say it's 2 times 58 degrees, which is equal to 116 degrees. So a single transformation then would be a rotation of 116 degrees. All right, so now you can do your homework.